we are still interested in this one. This is the pathway that we want to pursue. So right now I show you KMC snaps allowing me to go from here all the way to these structures. Okay. Couple of problems. There are some reaction that happens between those one when they are in the system, right? So you have now those kind of structures, they can start interacting with each other. Plus, there are some reaction that happen on this surface as they grow. So we should be able to keep track of those. Okay, so why molecular dynamics now? So I was able to grow, but now I need also molecular dynamics. DFT provides some property, but we talk always about a single configuration, okay? So you had the one benzene becoming whatever, phenol, for example. The real combustion is a vast number of molecules. And so this kind of understanding of this complex system requires averaging over many configurations. And so looking at statistical behavior, okay? So not just one pathway, on average, what's happening. So why molecular dynamics? What it does, it generates trajectory that sample the phase space. Monte Carlo samples the time, okay? Remember, we advanced in time with this. So space, this MD samples the configurations, so allowing for calculation of some of the macroscopic property that you might be interested. Sometimes people sample the nanoparticles or some soot particles, and they have idea of viscosity or any other property. If you want those macroscopic property, then MD is a way to generate that. So what it does, it gives you property of the collective behavior of many particles. So that's the main difference, not just one, many. So what we're going to do with MD is to move up from understanding of an individual reaction, so some small pHs, all the way to collective behavior. We can also capture the dynamic. And so the transition from this static energy, you have your benzene frozen somehow, and then you have your product. Instead, we can see how they evolve over time. And then the complexity related to the real world, because the dynamic nature of the combustion and the nanoparticle cannot be captured by one single method. Okay, so you need to have a variety. Sorry if I started a minute earlier. I don't know. Okay, so my only point is that once you have those bigger structures with the KMC, just one second for you guys. Once I have this kind of structures, now I grew with the KMC. Now those structures, they find themselves in the box. They can interact with each other, okay? And so we needed to also consider the whole system. So before I move forward, like yesterday, I distinguished between QM and QC, remember, quantum mechanics and quantum chemistry. I want to ask you, because some people say I am a modeler, or I am a simulator, or I'm running MD simulation, or I'm doing computation. What's the difference between modeling and simulations? People use intertwining. So modeling is the mathematical representation of a physical situation. Simulations is the procedure to solve those equations, the result from the module, from the modeling. So what is a model? Model is an idealization. And so its relationship to the real problems is like the map of London, if you want, tube trains, to the real tube train systems. It's a simplification, but one that captures certain essentials. This is our goal. Remember, we have a lot of details. We need to create a model here to predict. So the map maybe misrepresents distances and directions, okay, here. But displays the connectivity. This is good for a model. The quality or usefulness in a model is measured by the ability to capture some of the governing physical features of the problem. This is important because, again, when you choose a tool or you need to make some approximation, like I did before, you need to make sure that those kind of criteria are preserved. So all successful models somehow distort the inessentials in order to capture the features that really matter. Okay? At worst, a model is a concise description of a body of data. At the best, it captures the essential physics of the problems. Okay? And we want something that is also able to predict the behavior under conditions which have not yet been studied. So we will try to do that, and this is one of the things I want to talk about tomorrow. So today I'm going to give you more the molecular stuff, and then I will land saying this is a lot of data. I need to understand what's happening. I need to create my model. So I need a little bit of machine learning, and I need a smart way also to predict things that have not been seen before. So what I mean by that is that can I use machine learning to predict properties that are not in the database that is trained on? Okay. The simulation, differently, again, is solving the equation, and so numerically solve this one. So we're going to look at those two concepts, modeling and simulations, with the molecular dynamics simulation. So that's the reason. So first of all, molecular dynamics simulations, so those are the three people that got a Nobel Prize in 2013. So Karplus, you might have heard the Charms. Then you have Levitt and you have Warshall. So Levitt was one of the first to apply molecular dynamics to protein folding. This is in 1975. Karplus is very much known for many things, including the Charms software. And then, I don't know if this is a fun fact, but the Golem computer at the Weizmann Institute of Science is the one where they ran one of the first simulation. So Golem is an historical figure. But MD was the method they fundamentally advanced and applied to systems that were previously not possibly to computational treat them. And so they made possible to simulate the dynamics of molecular system beyond static structures. Okay. So what is molecular dynamics? Just a basic idea. What it does is mimic what atoms do in real life, assuming a potential energy function. So we talked yesterday a lot about DFT. Before DFT, I was talking about this potential energy, the interaction between atoms. So the energy function allows to calculate the forces experienced by atoms given the position of the other atoms. So if you are, for example, let's say that you are here, this is the position, this is the energy. If you know the force with which your atom interacts with other atoms, and you apply Newton's law, you can predict the motion of this particle. Okay, so somehow F equal ma. So let's say, oh, this is too complex. So the model is based on F equal ma. And so the atomic interaction calculates the forces that then calculate the energy landscape. Okay. So the goal is we need an algorithm to predict the position, the velocity, and the acceleration as a function of time. So you have F equal ma. You know the mass because you know the molecules that you're dealing with. You have information. Somehow you decide what is the energy between the atoms. You can compute the forces, right? That is the second part. What you want is A. You want the velocity. You want to know the dynamic. You want to see how things are moving. Simplify the system. So one thing I need to mention, and again, this is a little bit of math, but it's important, is that a system that contains n atoms has 6n values defining the state of the system. Okay? So you have 3n and 3n momenta. Each combination of those coordinates is a point in the phase space. And now, if we consider a property A, that is something that I want to compute, okay? So let's say the density of the system. A property that is described as a function of the coordinate and the momenta looks like this. So let's say that you have the average over time of these properties is a function of those xn dimensional phase space. And this is an important expression that you see here. It's basically telling what they call the ergodic hypothesis. The long time average is equal to the ensemble average in the limit of an infinite number of members in the ensemble. Okay, so your ensemble is big, and you should run for a long time, because that's the reality. You can run an MD for a long time. So you work under this ergodic hypothesis that basically changes the long time average to the ensemble average that you have in your systems. And so, in other words, in MD simulation, since we only simulate a single trajectory, right, of a system, we rely on this principle to calculate the macroscopic property. So we run an MD simulation for a long time, collect data on A, whatever property it is, at various points along the trajectory, and then compute the time average to estimate the experimental value. Okay? This is a little convoluted, but is an important principles that we leverage when we run MD. So you need to run MD on sufficiently long time. What I'm going to do is to give you some basic of MD right now, in terms of modeling, in terms of simulations, and then maybe today I want to talk about pitfalls for this method. What I have seen that are some approximations that you cannot do when you run this system. Okay, so molecular dynamic simulation generate a sequence of points that connected in time. So you have a trajectory of those particles, right? And so time average, another property, can be calculated through those mainly two equations. So the motion of a system through phase space is governed by Hamiltonian. Here, equation of motion. You saw yesterday also the Hamiltonian in the Schrödinger equation, if you remember. But anyway, this is R, and this is the momenta that you have. And so V, that is the potential energy function. So the Hamiltonian is composed of this kinetic term plus the V, the potential energy. Okay? So the kinetic energy is due to the momenta divided by 2m. So, and when you look at the Newton's equation of motion, you have those expressions. Okay? So this is the x is the length, and p is the momenta again, and that's recover F equal AMX. So in this, we brought the Born-Oppenheimer approximation. The electrons move much faster than the nuclei. QM solved the Schrödinger equation for static nuclei, if you remember. And MD, the nuclei experience electron as an average field. So it's another way to describe nuclei, electrons, and the atoms. Too much math. So what does it do? This is an example. But why do I need that? So you need to solve this equation. What I'm looking at is, again, the velocity. I need to see how they move over time, those species, independent of what you're solving mathematically. But in this case, I wanted just to give you an example of why this is interesting. If you have to look at a surface, and it can be also a surface of a nanoparticle, a surface of soot, and then there are gas phase species coming in, right? Well, what happens is that many things can happen. And if your goal is to develop a model that look at the surface of those nanoparticles, then you cannot just say I have a surface and I have some molecule coming in. Because what you have is that those molecules can have a different impact angle. That will impact also the collision that you have. They can have different energy coming in. Some are too fast, and so they'll bounce back. Others are slower, so maybe they will sit on the surface in this case. You can have different surface curvature, okay, the molecule that I started, and different surface energy and charges also on those structures. So bottom line is that this MD, like the example that I show you in this movie, given some initial conditions in which you have the mass, you have some knowledge about the forces and the energy between the atoms, they allow to predict how they are moving those atoms over time. So, and if you want, again, to be comprehensive in developing the model at this level, then those are the type of information for this surface model that MD can give you. Okay, so I glossed over the model, but we look at Newton, as I mentioned, and we look at velocity integration. Now, what do you do to perform the simulation? So how do I solve it? Remember, model is Newton. How do I solve this? Okay, so the first thing that you need to do is you need to decide the potential, how those molecules interact, okay? This is a priori information. You select the boundary condition, and you select your molecules. What is the initial velocity? What is the temperature? The temperature will dictate the velocity. What is the masses? Second, you will decide the ensemble. Remember, I am converting for the ergodic principles to an ensemble average, right? So I need to decide the ensemble, meaning the community that I'm going to sample, if you want. And then we need to look at some of those parameters, and then we perform simulations Usually what you do first an equilibration. So you slowly make sure that the system relaxes at the right condition that you picked, and then you run a production run, okay, to collect the thermodynamic average position, velocity, and then you analyze. So this is the thing. Now, this is important. It goes back to what we talked yesterday a little bit, the potential, the interaction. I need to choose my interaction model. It's one of the main inputs that you have. Now, potential energy can be divided between pairs, triplets, or particles. So this is an example. You have 3, and you have all those interactions. Okay? So you will have ij, you will have ijk, and you will have ijkl, and you keep going. So those are all the things. But you can also make an approximation that now this is a pairwise additivity. So I'm looking at ij, for example, and then I look at the contribution of all the pairs. So this is an approximation to simplify our problem. Okay? But you still need to have information on how those molecules interact with each other. And so usually the interactions are largely dominated by the pair terms. So you look just at the person on the atom next to you. Okay? So the ij, aj. And the true pair potential is usually replaced sometimes also by an effective pair potential, which incorporate many body effects. So you can be a little bit more accurate. So you look at the pairs, but you can also correct a little bit. Those are things that you choose in initial simulations, okay? So an example of interatomic pair potential, Lennard-Jones is another one as a Morse potential, but they are all, if you see, this is Rij, Rji, so this is the pair that you're looking at. Lennard-Jones, again, so this is the 2 molecules, this is the distance, and you have an attractive, this is the molecule separated, then you get an equilibration distance, and then if you push them together, they repel, right? And so an argon system, a box of Lennard-Jones molecule looks like this. So many simulations, many atoms in here, and you assume that this is the way they interact. So if 2 molecules get too close, meaning below 4 in this case, they will be repelled, right? If they are at 7, maybe they will get together eventually. So this is the way you describe the dynamic of the systems. What about the initial velocity? So now I say I have a rule. This is my rule for the forces between how you attract or repel each other. The second thing, I need the velocity. The velocity of the particle is related to kinetic energy, right? And so this is the expression you're familiar with the mass square of velocity divided by 2. The kinetic energy is also related to the temperature. So sometimes I want to look at an experimental system, and I want to do an MD. The experimental data that I have is the temperature, right? They measure the temperature in the system, for example. And so temperature is related to the velocity, that is related to the kinetic energy, K, and is therefore related to the velocity. So that's my input in the system, okay? You want to know how the atoms, what is the velocity of the atom at the beginning in that conditions. And then you can assign some velocity distribution, maybe according to the Boltzmann distribution. This tells you how the velocity is going to evolve, right? Or other systems. This is an example. Then the pool of molecules you are sampled from. So the more natural, if you want, ensemble. So ensemble is a large collection of atoms in this case. Is what they call microcanonical ensemble, NVE. So constant number of particles, constant volume, and constant energy. So you mean you're running your simulation, you have a box, you want to compute the density, just to give you a property. Then your box has constant molecules, constant volume, and constant energy. But experiments, usually they have constant pressure or constant temperature. So the flame that I was showing before, we use constant pressure. Or they have information about the temperature at different points, and I want to see my box, what happens there. Well, what you do then is changing the pool, and you look at NVT. That is a canonical ensemble, but this time you are keeping constant the number of particles, volume, and temperature. Okay? And then you can also have an isobaric, constant pressure. You can have a constant temperature. You can do different tricks. But the idea is that you need to think a priori how your experimental system looks like. You want to make sure that your input in MD makes sense. The last part for this input is the periodic boundary condition. Now, a real system contains 10 to the 23rd molecule simulation, okay? A lot. Our simulation may contain 100, maybe 1 million of molecules. So this is not reality, okay? I'm trying to stay as close as possible reality. And so a small cube, to give you an idea, when I say my box, because MD, what it does, you define your box. So in your box, you put, let's say, all those argon molecules. But you need to tell me how much is the volume of this box to a simulation. The bigger the volume, the more costly is the simulation. So there are a lot of tricks. And so this is my MD simulation, one box. But again, if you think 10 by 10 by 10 molecules, there's about half of the molecule on the surface. So what happens is that if it's too small, the molecules will go on the surface, on the walls, and they don't interact with each other also. And so what we do is periodic boundary condition. So you just replicate this initial box around. And so the small box replicated in all direction. A particle that leaves the box on one side is replaced by the image box on this other side. So if the red leaves here, you have this one, okay, that is coming in from the other side. And so basically there are no walls and no surface particles to these things. Okay, so how do we solve this? So now that we have some initial information, we decide what is the force between the atoms, what is the velocity, what is the temperature if you want, or periodic boundary condition. We need to solve the equation. Remember, we got to something that looks like this, in which you have Newton equations, and you need to look at the velocity, basically. So this is a system of ordinary differential equations now. For n atoms, you have 3n position and 3n velocity. And so the analytical solution is impossible to solve, but numerical solution can be straightforward in this case. And so here you can see a way to integrate the length, distance, and velocity, okay? So this is one of the algorithm that is usually for that. There is something that can get even more accurate. So you can see here for a velocity Verlet method is solved in 2 steps. And so what it does is basically they have, in this case, they look, if you are here, they look half before and half after. So instead of doing like delta t that is here, they are doing the velocity, for example, with I plus 1. Anyway, it's just a differential mathematical approach to solve these equations, okay? This gives a little bit of better accuracy over longer simulations. So instead of jumping 1 and 2, you're basically looking at 1.5, 3.5, and 1.5, okay? So you are integrating those equations over time, right? One other important thing that you choose is the time step. I will show in the pitfalls what happens. Now, you can say I want to integrate those equations every 10 femtoseconds or 1 femtosecond, for example. The choice you made influenced the property of your system. So here I want to show you, this is the total energy. So let's say that you're running an MVE. Remember, molecules, volume, energy constant. And I'm looking at the simulation over time. The energy is here. So what you see is some kind of energy that looks like this. And this is OK. So the time step that you chose allow you to conserve energy, you know, more or less. But there are situations in which your time step is too big. So if you want to cut corners, for example, and you say, I don't want to wait that long, I want a bigger time step, then there are many situations in which energy is not conserved. So one thing that to check is the energy is conserved in your system. So delta t that you choose is very important. Now, a too short time step leads to a very expensive solution of the equation. Yes, energy is conserved, but I can only run for a small amount of time my simulation because it's too consuming computationally. And that is also leads to a limited coverage of the phase space. But if you choose something that is too small or too large, you can lead also to instability here. Okay, so you have to be careful about what you choose. Now, great. Why we do this? What property can we compute. And I want to give you a couple of examples. Time average. So you can look at thermodynamic, energy, pressure, structural properties, or you can look also at dynamic quantities like time correlation function, transport property, diffusion. So if you're interested, I'm designing a new material, I want to know some of the structural property, how do they evolve over time? Or you are looking at the transport properties in your system, okay? You have some gas, you have another molecule, for example, you want to see how they evolve. Those are all properties that you can compute. So dynamic and time averages property. So let me give you an example, one of the most straightforward results that you can have. This is the environment. So I was looking at a simulation with sodium and A+ in water, okay, something that looks like this. So you have 512 water molecules and one sodium ion, the yellow ones. And so you run the simulation for a long time. The water molecules are readjusting themselves. Remember, there is also the potential, so there is a way to define how they attract or repel each other. And then the simplest things you can do is to get a snapshot. You can say, you know, around my sodium, the water molecules are arranging in this way. You can see some preferred attachment, how many attach, but be careful. This is one structure, okay? You need to sample multiple data points, something like that. You cannot tell me that the result is this, because this is one trajectory. You can get the structural properties. And so why this is important? So first of all, what they call a radial distribution function that gives a measure of the local structures. And so it corresponds, and I'll show you an example, to the local concentration of particles in a spherical shell, so here, at the distance r around a central particle. So what you see here is that the distance, so for 3 angstrom, you don't see anything, and then there is a peak. This is a liquid argon, so it means the other molecule is where the peak is, the probability. So an example. Let's say that you want to understand how, in those conditions, you have a box of water. How do those oxygen molecules arrange themselves? They are evolving freely, according to the potential, but you want to find a way. So what you do is looking at the radial distribution. So in this case, I'm showing you oxygen and oxygen, hydrogen, hydrogen, and oxygen, hydrogen. So the first one is showing you what is the probability, if you want, to find the oxygen. So how far is this oxygen, the next one. The next one is hydrogen, hydrogen, and then oxygen, hydrogen, oxygen, hydrogen here, okay? And so there is also this other one. So why this is important? Because it tells you how the structures evolve. So you don't find more of those structures far apart, but they're getting closer. And you can say something about the arrangement of those molecules in the system. So we did a study on alumina. I was interested in nanomaterials for alumina, not only carbonaceous, right? And one of the questions was, how do you go from an alumina bulk to something that melts? So this is an interesting problem that you can do with MD, but the reason why I'm bringing this up is because you can have this kind of property helping you. So if you run your simulations, you don't know exactly solid or liquid. You know a density initially, right? But then eventually over time, you can see that some particles are moving away. So you can think of a layer that slowly melts. We cannot define that in MD simulation, but what I can do is say over time, I can see that the distance between, for example, the alumina particle is going to get longer, or is amorphous, is less organized. So initially, at time 0, I have everything, like my oxygen is here, for example, but then after, I don't know, 1 nanosecond of simulations, I have the oxygen way farther apart, okay? And you can think of this with alumina, so you can see this rearrangement and melting of the species. So this is another way you can use this as structural information. Dynamic property. So those were like, this is more the average property that you look at. Now, what about the dynamic property? So this is a time correlation function. The correlation between two different quantities, so A and B, are measured using the time correlation function. And so they give you, I'll show you an example, a picture of the dynamic of the system. their time integrals are often related to the transport property. Okay. And usually there is the Fourier transforms related to the experimental spectra. So you want to reproduce a spectra experimentally. So that's the way you do that. You need a time correlation function for that. Or sometimes for this, you can have also the velocity correlation. So this tells you something about the velocity correlation function of hydrogen in liquid water, how this is evolving over time. Okay? Compared with your V0 that was at time 0. So let's go back. I give you a lot of information. The idea overall is that you're evolving the systems and over time, and you're using Newton equation. So the model is a classical mechanical model of atoms, and it treats atoms as particles with mass and position. The interaction between those atoms are described by a force field, and this force is a mathematical model of the interaction, the energy, and how they attract or repel each other. We will see in a moment also that you can break a bond, because up to now I just show you, a type of attraction and repulsion in which there is no bond making or bond breaking. And then Newton's second law of motion is the main principles. So the force on each atom is derived by the potential energy, and then the velocity, you can compute the velocity at the position over time. What is the simulation in MD now is the time evolution of the system interacting, or the atoms that are interacting, by solving Newton equation. And so it works by a discrete time step I was mentioning before. And each time step, what you do, this is basically the algorithm. The force acting on an atom are calculated based on their position. And then they are used to update the position of the atoms. And the process is repeated millions or billions of times. And then you develop a trajectory. Okay? What are the limitations? Because we talk about this, but in the end, what are all those limitations? Why we are not using MD broadly? Why I'm not using MD to go all the way from my pyrene all the way to soot? Okay, I keep growing that. Well, first of all, the simulation requires a short time step for numerical stability. And so one time step is like 2 femtoseconds, just to give you an idea. It's usually at times I would use it. But structural changes can take also over to nanoseconds or microseconds or milliseconds or longer. Okay, so you're getting with this MD some limitation of the time. Millions of trillions of sequential time step for nanosecond to milliseconds event, and even more if you're looking at slower ones. So this is challenging. 10 years ago, the simulation of 1 microsecond were really rare. 1 microsecond. Now, computer advantage have enabled simulation of 7 microseconds on GPUs. But the simulation timescale remain like a challenge. So, in order to enable longer time scale of simulation, this is a big research area right now for molecular dynamics simulation. And they involve, you can improve the algorithm, you can do some parallel computing, or there is also hardware in which you have GPU and specialized hardware for that. Another limitation is the force field. The force field, molecular mechanics are approximations, okay? They have improved over time, but there are a lot of limitations. So the way you describe the interaction is an approximation. Why time steps? Many time steps, as I said, there are millions and trillions. And so why are so computationally intensive? First of all, there is a lot of computation going on in each time step. Because what happened is that the interaction are dominated by this, in this case, no bonded interaction, and those act between every pair of the atoms. You remember the one I showed you at the beginning. So in a system of n atoms, the number of terms is proportional to n2 to the square. Can we ignore those interactions beyond some cutoff distance? So can I say my molecule here, I really don't care about there is water up here. It's an approximation that people do with the molecular dynamics, but you need to be careful. If you have van der Waals interaction, usually yes, the cutoff is great. The forces fall off quickly with the distance. But if you're interested in electrostatic interaction, if your system has charges, then usually no. These forces fall off slowly with distance. So when you set up an MD, or you review papers on MD, if you're, eventually, those are things that you want to pay attention to, how they set up those simulations. So how can I speed up an MD simulations? Well, I want to reduce the amount of computation per time step. So we want a faster algorithm. So faster approximate method to compute, for example, the electrostatic interactions. And some force field can be evaluated every other time step. That could be something that people are doing. We can reduce the number of time steps required in the simulation. I told you before also the time step is an important part. Or can increase the time step, but careful, for example, conserving other property like energy before. And then we can reduce, this is interesting, this is the amount of physical time that must be simulated. So this is a major research area that involves making the event of interest take place at a quicker time in the simulations. So metadynamics, that is another approach in MD, that's something I've been using for a long time. It basically applies some artificial force to pull, to make sure that you sample the whole systems. So this is something else that can do. Another thing that you can be doing is to parallelize those simulations across multiple computers. But keep in mind that splitting the computation associated with a single time step across multiple processors requires communication between processors, right? And usually each processor takes responsibility for atom in one spatial region, and the algorithmic improvement can reduce those communication requirements. So it's something that is done, but there is many things you need to pay attention if you do that. Redesign computer chips. This is another way to GPUs, graphic processor units, are now used for MD simulation. They pack more arithmetic logic on a chip, and then parallelizing across multiple GPUs, although it's difficult. Okay, so you do know. Several projects are in the community that design chips especially for MD simulation. So NVIDIA is one of those. And this pack even more logic into a chip and allow parallelization. So some takeaway from this. MD simulation bridge the gap between the quantum chemistry, the quantum level, and try to understand the molecular, they try to understand all individual molecules with the collective time-dependent behavior of large number of molecules. So I'm putting many molecules together and I'm seeing how they evolve over time, okay? Not frozen in space like we did with yesterday. MD works by simulating the motion of atoms and molecules over time based on Newton's law. And this allows for the calculation of those macroscopic properties. It's intensive, but also helps to address complicated dynamics of those phenomena. Okay, one simple type of simulation cannot address. So I've been using a lot when you start looking at those bigger pHs and how they interact. And again, as I mentioned, the time scale is small. So you run 1 nanosecond, 10 nanoseconds, whatever. But this is the time scale. And if you remember that, sorry, let's see, the graph I was showing you before, when you have some of the rearrangement, you are on that time scale. So one last information, and then maybe we can, let's see. And again, I don't want you to look at the equation too much, but I want to introduce this concept that I use a lot with MD. So with MD, I don't only look at the dynamics, okay, that I just showed you. I look also at the free energy. So it's the propensity of two things somehow to get together, somehow. Is one of the most important thermodynamics. You might know Helmholtz or Gibbs free energy. Okay, so the technique to calculate the free energy of a system are very useful, especially when you start critical phenomenon, phase transition. I was talking before about the alumina that goes from bulk solid to melting. We also, and so we have used a lot also in combustion, and I'll show you later. But you remember that you can never compute the free energy, absolute free energy. You can only compute the relative free energy. So briefly, but what I want to show you this equation is that if you have two states, so think about two molecules. So you want to look at A and B, what is the propensity for them to get together, okay? And so if you have two states, since the free energy is a state function, you can only consider the difference in energy between those two states. And so without too much math here, what you see is that this Helmholtz or Gibbs energy here is functional of Boltzmann constant, temperature, and then there is something related to the Hamiltonian, again, okay? And so something that MD can solve for you. And there are different techniques. So this is the integration over all possible momenta and position of the atoms, and this is the Boltzmann factor, the probability of being in a state with the Hamiltonian H. So this is an MD simulation. So this equation relates to partition function. That is something that I told you yesterday. So that is the number of accessible microstates for a given macroscopic state. So do you remember yesterday we did the two things? We look at first to say what kind of energy can be stored in an atom, and then I say partition function tells you how they are distributed for those systems. So you do something similar here. You look again at the partition function because you want to know what are the available states for these conditions. And so why I included free energy? Because thermodynamic and not just kinetics is important. So when you do MD trajectories, it give you the kinetic information, how things move over time. But I am also interested in relative stability of different states, okay? What is the most probable species that is formed? So if I have two nanoparticles, what is the propensity for them to stay together, to form a stable compound if they get together? I cannot run simulations of 1 millisecond, but I can tell you those two are worth pursuing because they are stable if they get together. It can help me with a direct comparison with the experiment. So those free energy values are obtained from simulation can be compared with experiment from, for example, calorimetry or binding assay or solubility experiment. Those are all simple things that you can relate to. And then they allow for prediction of molecular behavior that might be difficult to measure experimentally, okay? So think about two systems, and you want to know, I want to mix those two molecules. Do you think it's worth running a bad experiment? It might be expensive, or we just want to maybe screen with molecular dynamics. So what you will do is the free energy of those two, see how they get together in those conditions, what is the energy required, and then, narrow down your experimental pool and only maybe start with the one that are more interesting. This is something always to think about. Let's say that you give you a project, someone tells you what, I need a new clean fuel, okay, whatever. How do you start? Where do you start? Or they give you an experiment and they say, this is my molecule that, I don't know, is this good or not? So yes, you can run a bunch of experiments, and they are trial and errors. You can say, I can put my molecules here, I can compute the ignition delay, I can compute the Soot propensity, I can compute the density, viscosity. Think about an engine. An engine, you need to have some property of the fuel that you're using, right? Well, you can do that. Or you can say, let me help a little bit with some computational tools and start saying, if I have, these molecules, MD can give me the viscosity, can give me the density in those conditions. Those are initial properties if you don't have it. And then you can say, does this work in an engine? Like the fuel needs to have some of the ASTM regulations, so there is some boundaries there. So MD can help you screening those things. Another way, this is for those thermodynamic property, but go back to yesterday. You remember we talked about bond dissociation energy? If someone asks you, I have this molecule, what is going to be the reaction mechanism? It's complicated, of course. But you can start with the first step. You can say, look at all the carbon, hydrogen, carbon, carbon, and say, what is the energy to break them? Maybe you can look at the smallest energy and start from that as a first step. Then I will say, likely this is the first one to break. Let's go with the quantum chemistry. And you get to the modeling. So I'm trying to give you idea and option to use those tools interactively, and also always think that this is not about just combustion. You can expand them. Once you understand the tools, you can apply to different systems. So many times the students ask me, you know, the PhD students, what is for you a successful PhD student? Because when they try, you know, they come for an interview or visiting day, it's always like, oh, how many publications, what's the minimum to graduate? These are the questions I get all the time. And that makes all sense. There are some people who have a very rigorous, you know, number of publications is to be reached. What I care is that, publication of course, but the point is that you need to understand what you're doing. And so if, for example, your PhD is in molecular dynamics, I don't know, of this system, for example, I want you to be able to, by the time you graduate, to think broadly. And so if someone comes with a different problem, can you think if MD is good or not? So you are owning the tool. It's not just something that you understand the basics so that you can make the leap and go to another field. This is very important. Students, so for example, I had the students who did the MD simulations, and he was looking at fullerant and other gas phase species. So we were interested in this, you know, you grow, you start forming those first nuclei, and then there is gas phase species. How do they interact? Do they absorb on the surface? So he did a lot of simulation on carbon, hydrogen, and for fullerant. He went to work for LG, that basically was doing screens, and he was interested in some kind of polymer screen. And so he was doing MD of a polymer. Situation, conditions are different, but there is a way to rearrange that. I worked once with the Toyota. They were interested, you know, the question was, I have those seats in the car that if you have an expensive car, you can warm up in the winter, you know that. And so the question is, can you think of a material that has a higher thermal conductivity? Okay, this is macroscopic, too far from it, but what you can do is maybe start looking at molecular dynamic simulations, allow to compute the thermal conductivity of species. And so, for example, we talked about nanotubes, how the thermal conductivity changes when you have different lengths. And so you will do an MD. Of course, there are some tweaks that you need to think about, but the idea is the same. Can you move outside your field and think about something a little bit broader? That, what for me is really powerful when you work. So I'm going to show you in a moment, maybe after we take 5 minutes. You want to talk 5 minutes? Okay. Let's break, but I want to show you two more things. That this one I was asked specifically. So I had a colleague coming and say, you know, I am getting a lot of papers that that I have to review, and they have MD, and the people who do MD are very limited in combustion, so they don't want to. And so the idea here is that I want to give you some hints, and I want to tell you what if, again, you want to analyze an MD simulation, what we should look for, okay? Problems and pitfalls as you move forward in combustion. So let's take maybe, what is it, 5 to 11, sorry. Come back 5 after.